Well, let's just go ahead and get started on this. So I'm actually pretty excited for this one. Um, I want to talk today about Newton's laws, which most people have heard of. Um, but so the reason why I want to talk about them in the way I'm going to talk about them is because in every class that I've taken and actually every textbook I've read in like introductory physics, Newton's laws are just given, and I've kind of always wondered, well, okay, how do you get to them? How do you um, find Newton's laws? And so I really want to take an approach uh, that we might take in modern theoretical physics, where you don't have a theory to begin with, and you want to build a theory. Um, and so I want to show how that's done, as well as present Newton's laws. So how are we going to do this? How do we find Newton's laws? And the way that I want to do it is I want to consider symmetry. So symmetry. So when most people see the term symmetry, they think of something like I have some shape, and I can draw a line where if I, fold this over this line, or maybe I reflect about this line, the shape looks exactly the same, or the two edges line up, however you want to think about it. Now, this is a type of symmetry, but when we do physics, we typically talk about symmetries in a different way, or in a more general way, I should say. And that more general way is something along the lines of, if I have a system, so call my system this, I can do something to this system. I can act on it in a certain way, mess with it, whatever, called a transformation. Transformation. And when I say transformation, all I mean is I'm trying to change the system in a certain way. And if at the end of the day, if we pretend that this looks exactly the same, then we would say that this is symmetric under the transformation. So this is when I say symmetry, this is exactly what I mean. I take some physical system, I mess with it, I do something to it, I transform it, and at the end of that transformation, it looks exactly the same. So an example might be a square. So if I have a square, we have the same idea as we had originally of, I can reflect about certain axes, or I can fold about certain axes, however you want to think about it. Let me redraw this one. So all these are axes that I can fold around, and once I fold it, it looks the same, or the edges line up, or if we want to think about it as reflections, if I reflect about this axis, it always looks the same. But that's not the only type of symmetry that this has. I can also rotate the whole thing by increments of 90 degrees. So obviously, if I take a square and I rotate a square by 90 degrees, it's going to look the same at the end. Now, if I take anything that's not 90 degrees, then at the end of the rotation, the square won't look the same as it looked before. It might have edges up here, so it might look like that after some more arbitrary rotation. So it's not symmetric under a general rotation, but if I make sure that my rotations are by 90 degrees or multiples of 90 degrees, then it's going to be symmetric, along with these reflections. Okay, so this is the idea of symmetry, but in physics, we tend to want to try to represent our systems somehow with math. And so we should still be able to do all of this with the math. So we should be able to see where the symmetries arise in the math itself. And so to give a good example of that, let's consider a very symmetric object, namely a circle. So if I have a circle, this object has tons of symmetries. I can draw any axis that I want as long as it goes through the center of the circle. And I can reflect about that axis, and it'll stay the same. It'll be symmetric under all of those reflections. And I can also rotate by some arbitrary angle. Any amount I want to choose, I can rotate by that much, and it'll look the same. Hopefully that's obvious. So how do we see this in the math? So to do that, I want to draw some coordinates. I'll call them x and y, x and y, so that the origin is at the center of the circle. Now, in this case, since the origin is at the center, I can describe my circle by the equation x squared plus y squared equals r squared, where r is just the radius of the circle. So, okay, so how do we show these symmetries mathematically? It turns out that it's actually easier to start with rotations. So if I rotate the circle by some angle theta, and I'll show it rotating in this direction. So if I rotate the angle by some angle theta in that direction, we can see that it's kind of, it's exactly the same, as if instead I rotate my axes like this, where the axes still are at 90 degrees to each other, so each axis gets rotated by the same angle theta. So instead of rotating the circle, I've rotated the axes in the opposite direction, and it has the same effect. So I'll call these new coordinates x prime and y prime, and they just sit at an angle theta with respect to the other ones. So to show how this works out mathematically, I want to represent my old coordinates, our unprimed coordinates, in terms of our primed coordinates. So let's start with x. So if I have some point on the x-axis and the old x-axis, and I want to describe it in terms of the x prime and y prime axes, all I have to do is look at how much each of the new coordinates lie along the x-axis, the old x-axis. So let's start with x prime. So we can see that for x prime, this part here is what lies along the x-axis. So if I write this down, then I might say that x is equal to x prime, and just using our trig, we know that the side of our 90-degree triangle, which is adjacent to the angle, gives us a cosine. So I get x prime cosine of theta, but I'm not done, because there's a part of y prime here which also lays in the x direction, the old x direction. But it lays in the negative x direction. So I'll subtract it off, y prime, and now it's on the opposite side of the angle, so I get sine theta. Okay, so I can do a similar thing with y. So the x prime part, which lies along y, is that, which is positive because it points in the positive direction of y. So this is x prime sine theta. And of course this is the part of y prime, which lies along the old y-axis, again in the positive direction. So that's y prime cosine theta. Okay, so now all we have to do is plug these expressions for x and y into this equation. And it's kind of gross. It's not the most pretty thing mathematically, but we just FOIL everything out. And we find that something like x prime cosine squared theta plus y prime squared sine squared theta minus 2x prime y prime cosine theta sine theta. So this is from x squared. So it's just this equation here squared and FOILed out. And I will add to this down here y squared. So again, just FOILing everything out. This is y or x prime squared sine squared theta plus y prime squared cosine squared theta plus 2x prime y prime cos theta sine theta. And since r is just a constant, this all is still equal to r squared. So now, immediately we see that this term and this term cancel. They just go to 0. And now I have one term with an x prime squared times a cosine squared, a second term which is x prime squared times sine squared, and same thing for y. I can use our nice little trig identity that cosine squared plus sine squared is equal to 1. And what we find is that this, after simplifying, becomes x prime squared plus y prime squared is equal to r squared. Which, of course, is exactly the same as what we had here. So what this tells us is that I can rotate my axes here by any amount theta, right? Because this angle that we chose, this theta that shows up in all these places, was completely arbitrary. It can be any number we want. So I can rotate my axes by any value, and the equation that describes the circle always looks the same in the axes that I want, or that I choose. So this is the mathematical way that we see the symmetry. So we see that the equation describing the circle doesn't change after rotating coordinates. So this is explicitly how symmetries show up in the math. We can do the same thing with reflections, and actually now it's much easier because we know that if I say reflect, so this is my y-axis, this here is my x-axis. If I were to reflect about this y-axis, I'll just write down the equation again. Reflecting about y just means that I take x to minus x. Any value of x just gets mapped to its negative value. But since x is squared in our original equation, we have something like minus x squared plus y squared equals r squared, which of course this here is just x squared plus y squared is equal to r squared. So again, we see that our equations don't change under this reflection. But now this immediately tells us that the circle is symmetric under any reflection about an axis that goes through the center, because I know that I can always rotate my axes to something like this, x prime, y prime, And now I can reflect about this new y prime axis, and I know that I have x prime squared plus y prime squared is equal to r squared. Same thing happens. X prime goes to minus x prime. It's squared, so the equation doesn't change. So a circle is also symmetric under reflections about any axis which goes through the center. Whoops, axis which goes through the center. And so we see this arise in our math. So our math tells us both of these symmetries. Okay. So now, this is great, but in this particular case, we knew the equation beforehand. We knew the equation of the circle, and we wanted to show the symmetries that this equation exhibited, or that the physical system, in this case the circle, exhibited. But often in nature, or in reality, we know the symmetries, and we want to find the equations which describe that system. So, for example, we might know that electric charge is conserved. We know that the amount of electric charge in a system never changes. That's a particular type of symmetry. So I might say, okay, what theory can I actually write down which has that symmetry as a part of it? So we can see that just really quick in an example, how powerful this is in narrowing down what types of theories I can even consider. So say, again, I have just a xy plane, and I have some vector in this xy plane, which I'll call v. Now, this vector is described by two quantities. It's described so the vector is given by its magnitude, so its length, magnitude, which I'll put these bars around it, but it's also given by its direction, which I can just label theta, the angle that it is to the x-axis in this case. So now say I have a theory. I know my theory shouldn't change under rotations. So I have some physical system that I'm considering, and I know that physical system, say, looks like a circle in the case that we just had. Then I know that I can't have a theory which actually depends on theta, because if the theory depends on the direction that this vector points, when I change my axes, so I switch to some y prime and x prime, this theta here, so I'll call this theta prime, is going to be different, but the length is still going to be the same. So I know that the equations should only depend on the magnitude. So immediately, without even having to think of anything physical or anything like that, we can see how powerful considering symmetries can be when writing down a theory, because in this case, we've excluded an entire class of theories. All of the theories that we could ever write down which depend on theta are now ruled out. We can't use those as theories because we know a symmetry of our system. Awesome. So, how do we get Newton's laws with this? So for Newton's laws, we might want to do something like this, where we have rotation under, or symmetry under rotations, or maybe translations, or scaling, things like that. But none of these actually end up working out. And I can draw out a very simple example where I have a ball, or how about I have two, which are moving in some particular way. So we can see that if I try to rotate, this picture is going to change. If I move from, say, I'm here, and now I move over to here, again, this is going to change. It's going to look different. And if I now make myself bigger, it now, again, looks different. So we can't use any of these because we want some set of equations that describes physics in general. So in any physical system should have these symmetries. So I want to now to actually motivate the symmetry that we want to use to get Newton's laws. I want to talk about a subject that is very near and dear to my heart, because it was the first video I ever made, which is Galilean relativity. Relativity. Now, in my opinion, this is a very underappreciated subject in classical physics because of the fact that all of classical physics is built off of Galilean relativity, and I'll show you how. So what Galilean relativity says is that there's essentially some layer of subjectivity to our reality. There's different people can experience our reality in different ways. So let's give an example. If I draw out my two favorite people, Albert and Isaac. So this will be Albert and Isaac is standing on some cart, we'll say. We'll give him some fancy hair. So now both of these people want to measure the distance to some point. I don't know, maybe it's somebody's house. So they want to measure the distance to this house, but let's say that Isaac is moving relative to Albert. We'll give him some velocity, just call it v. Now, we can specify the different points of view by what we call reference frames. And like I said, the reference frame just specifies how the individual person is going to view reality. So we'll give this frame the label A, and this frame the label I. And the frame I is going to be moving along with Isaac. So now Albert is going to measure some distance to this house. We'll call it XA. Isaac is going to measure some different distance, call it XI. Now, say that when all of this started, so when time is at 0, we'll say t equals 0. T equals 0, we'll say that XA is equal to XI. Or in other words, this whole thought experiment starts when both Albert and Isaac are the same distance away. But Isaac is getting closer and closer to this house. So he is going to be measuring a different distance to the house than Isaac is. So they aren't experiencing reality in the same way. And we can account for that by the fact that Isaac is moving. So we can actually write in general, Isaac's distance that he measures in terms of the distance that Albert measures. Well, Albert's staying the same distance away, so his is just going to be some constant shift, or some constant that he measures. But since Isaac is getting closer, we have to subtract off his velocity times the time that he's been traveling, assuming that this velocity is constant. So, okay, so they measure two different distances, they experience reality in two different ways, but we have a way of relating the two. So now, let's say that this house is on wheels, and the house is now moving in Albert's frame. So instead of doing that, I'll say that Albert measures the house moving at a velocity VA. So that tells us that after some time, Albert measures the house a distance VA times t away, plus some x0. I will call this, x0 a. So the initial distance away from him that it started in his frame. So, and just to make things a little bit simpler, we'll say that he started on top of the house. So he started with it at a distance 0 away. So now, let's go into Isaac's frame. Well, we already know the rule for getting between the two frames, at least for the different positions that they measure in the frames. And so we just plug in the distance that Albert measures, minus this vt, where v, again, is the relative velocity between the two. Albert measures Isaac moving at velocity v towards the house. Okay, well, let's pull out an overall factor of t. So we get va minus v times t. So, since we know that positions are given by positions of constant velocity objects are given by the velocity times time, we can immediately identify this as the velocity that Isaac measures this velocity. So now we have a very good rule for getting between the two reference frames. So just to reiterate, I'll say we can get between reference frames by saying that any velocity, so this is any velocity that Isaac measures in his reference frame, is given by the velocity that Albert measures minus their relative velocity, specifically the velocity that Albert measures Isaac moving relative to him. Okay, so this is very important because, well, what have we done? We've started with some system in Albert's reference frame, and we've changed things to a new system. So this is a transformation. Specifically, this is a Galilean transformation between, and it takes us from one reference frame to another reference frame when they're moving relative to each other. Excellent. So, one thing that Galileo noticed is that you can't actually tell the difference between two reference frames in regards to physics as long as they're moving at constant velocities relative to each other. So let me clarify that a bit. So picture you're in a car. Let's see if I can draw a car. So you're in a car, and you have a ball. And say this car has, it has no windows or anything. You can't see out of it. Say it's a self-driving car, so that you're not endangering anyone on the road. So if I throw this ball up in the air, as long as the car is moving at a constant velocity, the ball is always going to come straight back down. That could be if the car is moving at 0 miles per hour, or it could be if the car is moving at 100 miles per hour. There's no difference, according to this person standing in the car. So we have something which tells us that the laws of physics, so in this case, the laws which describe how this ball is going to move once I throw it, should not depend on relative velocities as long as they're constant. Now, if this car is accelerating, then when I throw the ball, it's going to do something like that, and I'll be able to tell that it's accelerating. And this is, you know this because if you're sitting in a car and the car starts to accelerate, you feel like you're getting pulled back into your seat. So we have our symmetry. Our symmetry that we want all of our laws of physics to be symmetric under is constant shifts of velocity. So if I have some v, we'll say, v, and this could be v as a function of time. This velocity doesn't have to be constant. So this could be the velocity of the ball as it's going up, which obviously changes. But this should be my laws of physics should be symmetric if I just consider some change v minus v naught, where this is a constant. The constant part is very important. That's a very important part of this. So now I want to take a second and kind of catch our breath, see if anyone has any questions, and yeah. So if you have any questions, feel free to leave them in the chat. Feel free to do that at any time. Hi to Batfish. Glad you think it's interesting. I think it's interesting as well. But so, yeah. If you have any questions, feel free to leave them there. But so, yeah. We have a symmetry for our system. So it doesn't look like there are any questions. So if we have our symmetry, we can in principle now build some equations which are symmetric under this change. So I'm just going to reiterate our symmetry is this Galilean transformation. So shifts by constant velocities. So what can we use that isn't going to change under constant velocity shifts? Well, we have a couple of choices. One of them is that we just never have anything have dependencies on velocity. If velocity never shows up in our equations, then we can shift velocity as much as we want. Nothing's ever going to change. But unfortunately, I'm going to give this one a big red X because of the fact that it's boring. We don't care about this. We want to know how things move. We want to know how they evolve in time, and that's always going to have to do with velocity, how things are moving. Velocity is a fundamental part of motion, so if we don't have any velocity ever, then everything's just sitting in one place, and that's really boring to think about. So another case to think about is if we only ever have only velocity differences. So say I have two velocities, v1 and v2. All of my equations are built out of things like v1 minus v2, then when I shift by some constant velocity, all of my velocities get shifted by our Galilean transformation, minus v2 minus v naught. These two things cancel, and I end up exactly where I started. Okay, so this looks promising. We can have motion in our systems. But again, I'm going to give this a red X. Mainly because of the fact that in this case, we always need at least two velocities. Which we don't always have. I can consider a single ball, moving along at some velocity, and I should still be able to describe that. But in this particular case, I can't do that because I don't have a second velocity to take the difference with. So, a third option is we only have equations which depend on derivatives of velocity. So in this case, if I have dv dt and I shift by some constant velocity, then I'll get something like d by dt, and where this velocity could be a function of time, this regular v, I shift by some constant velocity. The derivative of a constant is always going to give me 0, and I'm back right where I started. Now this is much more interesting. This is quite a bit more interesting to think about because we can have a single velocity. We have time evolution built in because this derivative with respect to time tells us how the velocity changes with time. I assume time derivatives here because v is typically only a function of time. So this looks much more promising. So let's go with this for the time being. And I'm going to just define some new thing, which is p. I'm just going to give it the name p. And it's equal to some alpha, which is just constant specifically in time. And the equations which describe physics, I'll just give it the name F. We'll see why I'm giving it these names later. And it's just going to be the time derivative of this thing, this object. So obviously, if alpha is a constant, I can still shift velocity, and I can take d by dt of alpha v, shift v by some v naught, and I get d by dt alpha v minus alpha v naught. Since both of these are constants, this is going to go to 0, and I have d by dt alpha t, or alpha v, which is great. So in this case, this here is the equation which describes all of physics, all of the physics that does not depend on these constant frame shifts. So, or in other words, this takes the subjectivity out of reality, because this tells me stuff that is completely independent of the reference frame that I choose to be in. Okay, great. So do we have any questions about this? Give people a little bit of time to answer. Hopefully you guys are as excited about this as I am. Okay, I'm not seeing any questions show up. So now the question is, what the heck is alpha? What do we choose? I mean, this is some value that we've introduced that we sort of have the freedom to choose. So again, let's consider a few options. So the first is probably the simplest, in which case let's just set alpha equal to 1. So then this tells us that p is just equal to v, and f is equal to dv dt, which is acceleration. I'll just acceleration. Okay, and this works. This works fine. If you saw the last stream, we did plenty with this. We considered dropping a ball off of a tower, only considering the acceleration, and we got physics out of it. So this could work, but the problem is, the nice thing about gravity, at least Galileo's version of gravity, is that it pulls every single object with the same acceleration. This isn't always going to be true. So if I push and pull on different objects, they're going to accelerate at different rates in general. So if I try to use this, different objects can accelerate at different rates. And this actually isn't that great, because of the fact that if I have some more general push or pull on my object, I'll need to know the acceleration of that particular object. But that doesn't necessarily give me any information about the push or pull on a different object. So in general, I'll have to measure the accelerations on every single object that I'm interested in which case I lose a lot of predictivity. I can't predict as much as I would hope with my theory. So while alpha equals 1 is perfectly valid, it's not the most convenient. So to think about what the most convenient thing is, let's think about what alpha has to satisfy. Well, we know that alpha is a constant for the full system, and we also should have alpha is something that is shared, or not necessarily shared, but every system has it. So I should be able to assign a number alpha to any system that I care about, or any system that I want to look at. So in classical physics, at least, there's something that satisfies this, and satisfies it very nicely, that being the mass of a system. We know that mass, well, if the system that I'm considering is all of the matter in a system, I can move around the mass. I can take it from point A to point B, so I can have some nebulous gunk of stuff full of some particles, and I can move that gunk around. But now that I say this, I should make sure to keep the number of these dots the same. The total amount of mass in that system should never change. So we've satisfied this, and everything has mass, at least according to classical mechanics. So it satisfies this. So we'll call alpha the mass of an object. And another nice thing about giving alpha, or identifying alpha with a system's mass, is that now I have a very nice interpretation of what this P is. So let's consider if I have two objects, one very small object and one very large object, moving at the same velocity. So they're both moving at velocity v. Well, this object here, so I'll call this 1 and 2. This one will have mass m2, m1. Then the p value corresponding to object 1 is going to be less than this p value of 2. In a similar way, I can consider two objects with the same mass, but in this case, this one will be 1, this one will be 2. I'll say that V1, V2, V2 is greater than V1, and we see a similar thing, that P1 is less than P2. Well, in both of these cases, the second object, so object 2, is harder to stop. So if it's much more massive and moving at the same velocity as a much less massive object, it's going to be harder to stop than the less massive object. If I have two objects which are exactly the same mass, the one that's moving faster is going to be harder to stop. So this gives us a very nice interpretation of P, which is how hard it is to stop the object. That's how we can think of this. And we give it the name of momentum. And obviously P stands for momentum. Okay, so now let's interpret our equations which actually govern physics. So this is F, which is dp dt. Well, we know that a derivative is essentially telling us how much this changes when this is changed a little. Okay, so this is telling us essentially how much our momentum is changing in a little amount of time. So again, we have a very nice interpretation of this, and that F is basically, I'll actually write this a little lower. F is how hard we have to push or pull to change the momentum, and typically it's the velocity that we're talking about, velocity. If for m fixed, so if the mass isn't changing, then really I'm talking about how hard I have to push or pull to change the velocity of an object in a given amount of time. And this we just give the name of force. And so here the F actually makes sense. Okay, so now I'm just gonna rewrite this. We have that the force is equal to the change of momentum with respect to a change of time. And this is pretty much all of classical physics. We can do all of classical physics with this one simple equation, which is pretty amazing. And actually, this is all three of Newton's laws tied up into one nifty little package. So again, I'll just pause here really quick to see if there are any questions before I get into like the specifics of Newton's laws. So we've done something really cool here, right? We've derived Newton's laws just by considering symmetry. And this is how a lot of modern theories are actually built. Like I said, we know a symmetry exists in nature, and we want to describe it using equations, or describe systems obeying that symmetry using equations, and so we can write down the equations. Okay, not seeing any questions again. Okay, so now let's talk about Newton's laws. Start out with his first law. And to get Newton's first law, all we have to consider is F equals 0. So in the case that F equals 0, remember again, dp dt must also equal 0 then. But I know that the derivative, the only thing that I can take the derivative of to actually get 0 is a constant. So this immediately tells me that momentum is constant if there are no external forces, so no outside forces. Or in other words, an object in motion will not only stay in motion, but will keep the same motion, assuming fixed mass, unless acted on by an outside force. This is the Newton's law that most people know. Object in motion will stay in motion unless acted on by an outside force. And same with an object at rest. An object at rest will stay at rest unless acted on by an outside force. But we know that those two statements are the same, mainly because we can always shift our velocity such that an object which is stationary, or an object at rest, now looks like it's moving, due to our Galilean symmetry. Okay, but this isn't the only thing that Newton's first law implies. So if I have a bunch of particles, so I have a bunch of these guys here, they're all gonna have their own velocities and their own momenta associated with those velocities, so that the total momentum, P I'll write it as P total, is going to be equal to the sum of the individuals. So if I label these as 1, 2, 3, 4, 5, 6, dot, 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 I might have much more. But the total momentum is always equal to the sum of momenta. So if I now apply Newton's first law to this, I find that dp total dt equals 0 for F equals 0. So if I don't apply any forces on my system, then the total momentum can't change in time, which means that the sum of momenta is equal to a constant. In other words, the total momentum of my system is always conserved unless I act on it with a force. Okay, so let's take an example of this. So I'll have 2 chunks of clay which are moving towards each other. We'll say this one over here has a mass m1, this one over here has a mass m2, v1 and v2. And so they fly towards each other, they collide, and then they stick together. And they'll have some final velocity, which it could be in either direction. I'll just draw it in this direction for right now, once they stick together. And of course the final mass is going to be the sum of the 2 masses, because all of the mass sticks together. So we know that the sum of my momenta, sum over I of pi is equal to a constant, which means that the sum over I of pi in the initial has to be equal to the sum over I of pi in the final state. So the sum of these 2 momenta has to be equal to that momentum, because there's only one object. So another way I'll write that is P1 plus P2 is equal to PF, where P1 is the momentum of this guy, P2 is the momentum of this guy, and PF is the momentum of the final lump. Okay, so now, if we want to determine what this final velocity is, well, that's pretty straightforward to do. We just plug things in. m1v1 plus m2v2 is equal to, well, we know the mass of the final state is just going to be the sum of the masses, vf, and now we just solve. Vf is equal to m1 plus, m1v1 plus m2v2 over m1 plus m2. So pretty cool. Again, we're able to do a physics problem. We're able to make a prediction about a system just using these equations that we derived solely based off of symmetry. So then, of course, we can go and test this, grab 2 lumps of clay, throw them at each other, and see if we get the right result. Okay, so now let's talk a bit about Newton's second law. So the second law basically says if m is fixed, then F equals d dt of mv, which I can pull the m out of the derivative, m dv dt, and dv dt is equal to the acceleration. So F equals ma is Newton's second law, or as it's sometimes said in words, the acceleration is proportional to the force acting on the body. Okay, so let's think of an example of how we might be able to make this useful to us. So remember what I said earlier about how we can't necessarily determine accelerations for any object. So how do we do that for forces? Well, there's actually a really nice way of doing this. So consider a spring. So I have some wall here, and I have some spring attached to an object which has some mass m, and we'll say right here is if the spring is completely relaxed, it's not compressed, it's not extended, that's where it wants to sit. And so now I extend this by some amount, call this x, and then I let go. Obviously, the ball is going to, or the mass is going to oscillate back and forth. It's just going to go back and forth and back and forth. And if there's no friction or anything to damp out the oscillations, then it's just going to go on forever. And so I can describe this displacement from this relaxed position as some sines and cosines. It doesn't really matter the exact form of it right now. Cosine omega t, where a and b are just constants that have to do with how far I'm pulling this mass. And omega is the frequency, so essentially how fast this thing oscillates back and forth. Okay, so now I want to find the force that the spring exerts on the mass at any given time. So I have to find the acceleration. Well, we know that the acceleration is equal to dv dt. We know that velocity is the time derivative of position, and so this is just the second derivative of position. So we have to know how to take derivatives of sines and cosines. Well, if I take the derivative of sine of omega t, I get omega times cosine omega t, and if I do the same for cosine, I get minus omega sine omega t. And these you can just look up. Okay, so now I need to take two derivatives, sine and cosine, and when I do that, I take d2x dt squared, I get something like minus omega squared a sine omega t minus omega squared b cosine omega t. And you can see that this has to be the case because once I take the derivative of sine, I get positive cosine, and then I take another derivative of that, and I get back to minus sine, and same thing with cosine. So this is actually really interesting because I can write this back in terms of my function for position. This is just a constant times my original position function. So this is just minus omega squared times x of t. So the force acting on this, we know, is the mass times the acceleration, which I can rewrite as minus m omega squared x of t. Now I'm just going to define some new thing, some new number, k over m, so that this right-hand side becomes minus kxt. And this is known as Hooke's law. And it basically tells me that the force is proportional to the displacement of the spring. and it always works in the opposite direction. Which we know from this minus sign here. So if x is positive, if I'm pulling the spring, the force is pulling it back towards the equilibrium position. So we'd call this a restorative force, because it always wants to restore to a particular state. Okay, so now this is very cool, because since I know this relation here, I can find k by taking a mass that I know, only one mass. I only ever have to do this for one mass. And I pull the spring, let it go, and let it oscillate back and forth. Well, I can measure omega for that mass, and assuming I know, well, once I know omega, and I know the mass, I can find k. And k doesn't depend on the mass of the object. It's just something that's inherent to the spring. So once I measure this for a single mass, I know k, and I can apply it wherever I want. So for example, if I hang a ball or a mass from the ceiling and let gravity act on it, you have some g acting down. But I'm also going to have some spring force acting up. And let's say we let this settle to a point where it's resting. Well, since gravity is pulling down on this, the spring is going to be extended. It's going to be extended from where it wants to be, assuming no extra forces are acting on it. So we'll call this some distance minus d, because we'll say that downward direction is negative. So, okay, the ball isn't moving in this case, so we know that there's no force, no total force acting on this, because the total force is going to be equal to the mass times the acceleration. It's not accelerating because it's not moving, so we know that this is equal to 0. But there are individual forces acting on this, one of which being minus mg, the mass times the acceleration due to gravity, so that's just this force here. And then we also have plus F spring, which is minus k times the displacement. So yeah, minus kx, but we know that x is equal to minus d. So this is plus k times d. Okay, so what we can do is, if we know the mass that we're hanging, if we know how massive that is, we know k, we've already measured k, say, we can measure the displacement, in which case we can find the acceleration due to gravity. This is kd over m. So we can use this principle to find forces, how hard something is pulling on an object. We can use Hooke's law to measure that, and that's how a lot of the times it's done. You have some object which you hook to a mass, and you let your force act on it, so whether you pull it or something else pulls it, there's a spring inside. The spring constant for that spring is known, and the computer just calculates it based off of the distance that the spring gets stretched. So that's how forces are typically calculated or measured. Okay, finally I want to talk about Newton's third law, which again I want to consider what happens when F is equal to 0, and there are two particles. We'll say that they have momenta p1 and p2. Well, we already know that dp total, dt, is equal to 0 because there's no outside force acting on this. But this is going to be equal to dp1 dt plus dp2 dt, because the total momentum is the sum of momenta. So I can then just, I can just rewrite this dp1 dt is equal to minus dp2 dt. So if I ignore either one of these equations, each side looks like a force. But since there's no outside force acting on this, the only forces that can be happening are between the individual particles. So maybe I have two electrons, and they're repelling each other. Their electric charge is repelling each other. That's one example where this might happen. So there's some force between the two, but it's not an outside force. It's coming from the system itself. So let's call this left-hand side. We'll say this is the force of particle 2 acting on particle 1, and this is equal to minus the force of particle 1 acting on particle 2. Because if I just ignore one of the two particles, it's going to look like there's a force acting on the other particle. So this tells us that if one particle exerts a force on another, another, the other must feel an equal and opposite force. So opposite coming from the relative minus sign, meaning that the two feel the same force, just in opposite directions. So a quick example of this is you're standing on the ground, or you might be sitting in a chair right now, whatever it may be. The force of gravity is pulling you down with some mg, but you're not accelerating, which means you're standing on the floor, which means you're pushing into the ground with that same force. But that means that the ground has to be pushing back on you with the same force, mg, just in the opposite direction. It's an equal and opposite force. That's why you don't go accelerating through the ground, even though there's a force acting on you. There's an equal but opposite force acting in the opposite direction, so that you don't experience any total acceleration. And this is just called a normal force. Normal because it always acts perpendicular to a surface. And I'm sure I'll talk about the normal force quite a bit in the future. So let's think of a less trivial example of being in an elevator. So when you're in the elevator, if it's moving at a constant velocity, we know that that's the same as it not moving because we can shift our reference frame. And the picture is the same as here. You're pushing into the floor at some acceleration mg, or force, some force mg, and the floor is pushing back on you. But now let's say we start accelerating the elevator. Well, the elevator has to accelerate you along with it, which means that now you are experiencing, I'll call this Fe. So it's already pushing with the force of gravity because it has to keep you from falling through the floor. But now it has to pull you along with it with the same acceleration. So it has to push you with a force ma. But what you feel is a force in the opposite direction. So I'll say F that you feel minus mg minus ma. And I'll just rewrite this as mg plus a. Well, this is the same thing as if we just had some different acceleration due to gravity, which is bigger than the normal acceleration due to gravity, or it might be less. if the acceleration is downwards, but in this case, we're pulling the elevator up. But this is exactly why you feel heavier when an elevator starts to go up. The elevator starts accelerating, and it has to push you up. You feel an equal and opposite force going down, which your brain tells you is a stronger force of gravity, so you feel heavier. It's pretty cool stuff. All right, so I want to do one last example that kind of pulls all this stuff together. But before I get to that, first I'll ask if there are any questions. And while you're typing any questions that you might have, give people a second actually before I ask this. I'm going to ask you a question. Okay, again, I'm not seeing anything popping up. So I'll pose my question that you can think about while I'm doing our last example. So again, if you saw the last live stream, you saw something that we considered where we had a ball experiencing air resistance. So it had some acceleration, so we had the normal acceleration due to gravity, but it also had some extra acceleration, which was proportional to the velocity. So what's the force acting on this? The force is, of course, equal to m times g minus m times alpha times v of t. Now, alarm bells should be going off right now because of the fact that this, we know the left-hand side, because we built it to be such, it doesn't change with shifts of velocity, of v. So I can take v to v minus v naught, and the left-hand side doesn't change. But look what we have here. We have velocity showing up. So it looks like if I make this change, I'm going to get something like v of t minus v naught, and the right-hand side is no longer invariant under our symmetry, or it now changes under our symmetry, which makes us very sad, because it seems like we're getting a contradiction. So my question to you that I want you to think about while I'm going through the last example is, what assumption did we make here that breaks down when we shift velocities? And how can we change this so that the right-hand side is symmetric and consistent? So how can we change this equation? So I want you to think about that while I'm going through the next example, and then I'll come back to it at the end. Okay, so the last thing that I want to talk about, I kind of want to pull together all of Newton's laws. And to do that, we'll think about a rocket ship. Let's see if I can draw a rocket ship. Which is flying through space. Well, we'll say that originally it's not moving. We know that we can always shift our velocities so that it looks like it's not moving. So its velocity at time t equals 0 is 0. But then we're going to have it turn on some thrusters. And these thrusters, what they do is they're going to throw mass out. So I'll call this mass exhaust. And the thrusters are going to throw mass out at some exhaust velocity, call it VE. And they're going to throw it out at some rate r. So the amount of mass that this thing is losing, so we'll say at the mass of the ship at time t equals 0, we'll say is m naught. And we'll say that it's losing mass at a linear rate. The rate we'll just call r. So ms of t is going to be the starting mass, and we're losing mass proportional to time. Now, since we're throwing mass out, that mass has to go somewhere. So that mass is gained by we'll call it the exhaust mass. We started out with 0 exhaust mass. And so we're just gaining exhaust mass at the same rate that we're losing the mass of the ship. Because the total mass has to be conserved. It can't disappear into nowhere. We have to account for it. So if it's just floating around in space or flying through space, there's no outside forces acting on it. So I'll call this force external. So there's no like gravity, there's no weird springs or anything like that acting on the ship. Everything is internal. Everything is our system essentially acting on itself. So we know that P total, or the derivative of P total, is equal to 0. But we know that there's two components of the momentum. There's the ship's momentum, and there's the exhaust momentum. So we'll call this dPe dt plus dPs dt. And that has to be equal to 0. And so let's just go back to Newton's third law. And all it's telling us is that any force that the exhaust feels from the thrusters, the ship has to also feel in the opposite direction. This is how rockets fly. This is how rockets go anywhere. Okay, so now this gets a little complicated because of the fact that P sub s, the mass and the velocity, v sub s, are functions of time, which means we have to use the chain rule when we take our derivative. So the first times the derivative of the second plus the derivative of the first times the second. And now the exhaust velocity is the mass of it is changing, but since we're always shooting it off at the same velocity, then that's actually a constant, which tells us that dPe dt is just dme dt times the velocity of the exhaust. Okay, great. So now we can just set these equal to each other, but before we do that, let's actually take these derivatives. So we don't know dvs dt. That's what we want to find. We want to find the velocity of this ship after some time. But we know that ms of t is equal to m naught minus rt. So dms dt, the constant term drops out. We know that this is raised to the 1. We subtract 1 from the power, multiply by the old power, and we get that this is equal to minus r. And we can do the same thing for the exhaust mass. So dme dt, this is equal to plus rt. So we get the same thing, just without the minus sign. So what do we find? We find that ms of t times dvs dt, which is just m naught minus rt, this guy here, times dvs dt, minus r times vs is equal to r ve. Okay, so now let's just go ahead and put everything that isn't the derivative of velocity, or the velocity that we care about, on the right-hand side. So dvs dt is equal to, factor out a total r, vs of t minus ve, or plus, divided by m naught minus rt. Okay, this looks pretty messy. This looks like a total disaster. But let's use a few tricks. The first of which, we'll say that vs, we'll redefine vs of t to some new function, call it u of t, our favorite trick, minus ve, so that this ve here cancels with that. Well then dvs dt, the derivative of a constant, is 0, so this just gives me du dt, so the left-hand side is unchanged, du dt is equal to r times u of t, divided by m naught minus rt. And now I'm going to treat these guys as independent differentials, multiply both sides by dt, and I'm going to divide both sides by u. So I get something that looks like du divided by u is equal to r dt over m naught minus rt. Okay, we're almost there. This still looks a little bit messy, but let's make one more shift in, this time t. Let's redefine what t is. And we'll call t 1 over r, mainly because we want to get rid of this gross factor of m naught. We'll say this is 1 over r times some new variable, we'll call it tau. And this will be plus m naught. So you see when I plug this in for t, this r and that r drop, this m cancels with that m, and I'm left with something which looks substantially simpler than I started out with. Oh, I should also say, when I have a differential, I can multiply this by a factor of 1, d tau over d tau, just changing around where the differentials lie. I can call this dt over d tau times d tau. Taking the derivative of this, well, this guy is just a constant. I have a constant times the variable that I'm taking the derivative with respect to, and so I just get the constant out. So I get 1 over r times d tau. You can see that this 1 over r cancels that r, so we actually have a very nice expression, which is equal to minus, coming from this minus sign here, d tau over tau. Okay, so now all we have to do is integrate both sides. Talked about last time, the integral dx over x is log x plus c. C is a constant. And so I can lump the constants together into a single one, which I'll just give the overall name of c, and I'll just arbitrarily put it on the right-hand side. So I get something that looks like log of u, and this is some function of tau, is equal to minus log of tau plus c. I can use log rules to rewrite the right-hand side as log of 1 over tau plus c. And now I just exponentiate both sides. So I raise both sides, or raise e to both sides. I'm going to say some new constant k is e to the c. And we can see that I get something like u of tau is equal to k over tau. So now we just plug things back in, rewriting my expressions. I had v sub s is equal to u t minus VE, and I had that t is equal to 1 over r times tau plus m naught. Shifting things around, tau is just equal to RT minus m naught, if I'm not mistaken. I feel like I'm off by a factor. Oh no, I think I'm good. Okay, so in this case, I have Vs of t is equal to my constant k over RT minus m naught minus VE. I can multiply this by RT minus I can multiply this by the stuff in this denominator here divided by that stuff in the denominator, so a factor of 1. So I multiply this by RT minus m naught over RT minus m naught. And this gives me something which looks like I'm going to pull this minus sign into the denominator here. And this looks like RVET plus k prime, which is a new constant, I'll define it in a second, m naught minus RT, where k prime is just a bunch of constants lumped together. Since they're all constants, I don't really care what I call it, but this is minus k minus m naught VE. So we are so close. All we have to do is determine k, or k prime, in which case we know that at time t equals 0, Vs is 0, and so we just plug 0 in, and here we get 0, here we get 0, so we get k prime over m naught, which tells us that k prime is just 0. So we have our equation for how fast the rocket is going at any given time is equal to, I already forgot what it was, RVET over m naught minus RT. So now let's notice something real quick, in that this is also equal to RVET divided by the mass of the ship at any given time. So if the mass of the ship was fixed, then the velocity would increase at a steady rate, a constant acceleration. But we're losing mass. So essentially we can think of this as the acceleration is getting faster and faster and faster because we're losing mass. But that's exactly what we expect. The thrust from the rocket is always going to be the same, and we know from F equals ma that, well, just rearranging, a is equal to F over m. So if my thrust, in this case, so how hard the rocket pushes the exhaust out, that never changes. But the mass gets smaller and smaller, so this drives the acceleration up, and our velocity increases at a faster and faster rate, which is exactly what we would expect. Now, before I show plots of this, we should check one quick thing, and that is that the conservation of momentum isn't destroyed. So we know that the momentum of our ship is the momentum of our ship at any given time is equal to the mass of the ship times the velocity of the ship. Well, as we already wrote, the velocity of the ship is related to the mass of the ship, so that actually cancels out, and I just get something which is RVET. Now, oh, sorry about that. The initial velocity of our ship was 0, so its initial momentum was 0. So we know that the total momentum always has to be 0. So if we write this out, we have r vet plus m e, the mass of the exhaust, times the velocity, but it's going in the opposite direction of our ship. So we'll give this a negative sign because we'll say that the velocity, so the ship is going this way, so my ship here is going this direction, this is plus, velocity of the exhaust is going that way, that's a minus. So I'm going to actually put a relative minus between these two, just coming from this. But the exhaust mass is given by r times t, the rate that the ship is losing mass times the time that it's gone. So we get something like RTVE, which is equal to 0. Our momentum is always conserved. That's very good. So again, I'm going to switch to the plots. Warn you, because the plots are going to be kind of bright. Okay, so here's what this looks like with respect to time. So time is the, I'm going to make this a little bit smaller. Time is on the horizontal axis, the velocity of the ship is on the vertical axis, and we can see that as I shift, so I can increase the rate that we lose mass at, and you can see that it takes less time for the ship to get to a high velocity. Similarly, I can change the initial mass of the ship. Again, it takes less time. So if I decrease the initial mass of the ship, then we get up to speed faster. If I increase the mass of the ship, then it takes longer, which again makes sense because the force is always the same, so the acceleration initially is going to be slower. And now I can crank up the exhaust velocity, which just shows me that, again, I'm increasing my speed faster because I'm throwing the exhaust out faster. And most importantly, we see a asymptote. We see that this doesn't go on forever. There's a point where the velocity essentially becomes infinite. And that's just the point where we've lost all of the mass of the ship. And obviously, at that point, the acceleration effectively becomes infinite because we have force over mass, and so naturally our velocity also becomes infinite at that point. So we see exactly what we would expect. Good stuff. And of course, this crashed again. I don't know why it does that. I need to figure that one out. But okay, so there's that. So let's go ahead and see if people have questions, and if not, we can talk about the question that I posed and then wrap up. So yeah, I think this is pretty cool that we're able to derive Newton's laws in this way, and then use them effectively. Okay, so again, I'm not seeing any questions, and if you want to put your answer to my question that I posed in the chat, you're welcome to do that as well. But I'm not really seeing anything. So let me talk about it. So let me write down this equation again. Minus mg minus m alpha v of t. So we made a assumption here. And that assumption is that the air is always not moving. So if I'm throwing a ball, or say I'm dropping a ball, Um, what I'm saying is that the air that's acting on this is never moving. That's the assumption that I made. It's not a good assumption, because of course I can shift my velocity by some amount, and I'm going to see all of this air moving in the opposite direction, right? This is, if you've ever stuck your hand out of the window of a moving car, you know this. It feels like the air is moving backwards. So, to fix this equation, what we can do is we can just write minus mg minus m alpha v of t minus the velocity of the air. So then we actually care about the velocity difference between the ball and the air. And this actually makes a lot more sense to consider, this value here, because the velocity of the ball is subjective, as we've already seen, but so is the velocity of the air. So what we really care about is how fast the air sees the ball moving. And so that's exactly what this difference is telling us. In which case, we can now make our velocity shift, and this term here, we just get v of t minus v naught minus v air minus v naught. And again, these guys cancel, and we get back to exactly what we had before. Everything is invariant under Galilean transformations, or it doesn't change, it's still symmetric, and nothing is actually broken. We just have to be careful about the assumptions that we're making. And so, with that, I think that's everything I want to talk about. So, if there's any finishing questions, feel free to ask them. I'll give you a little bit of time to do that if you want. Okay. Not really seeing anything. So, yeah, again, I'll say thank you for watching. Thanks for everybody who tuned in, and if you're watching this after the fact, I appreciate it, and I hope you enjoyed it, and I hope you learned something. All right, thanks.